Very good morning to one and all. So myself, Dr. R. Sindil Kumaran, Assistant Professor, the Department of Electronics and Communication Engineering from SRM Institute of Science and Technology, Katamguttur campus. So in continuation with digital circuits, today's part we are going to discuss about the very important topic, the sequence detector. You know very well. So the finite state machine, we will be having two things in the two classification, Mealy machine as well as the Moore machine. So uh, here we are going to discuss either by melee or it may be of more, irrespective. If in the question it was not specified, we can go for either melee or more, right? Right. So today this diagram indicates we'll have two overlapping detector. So the first thing is of overlapping detector and the second thing is a non-overlapping detector. Let us see what is meant by overlapping as well as the non-overlapping. So this was the question, right? Design a circuit that detects three or more consecutive ones in the input line. So we have to design a circuit in such a way, if the three consecutive ones arrived at the input line, then the output will be of 1. Okay. So okay, so let it be of, for example, let it be a input sequence 1 1 1 0 1 0 1 1 0 1 1 0, or include 1 here, right? So in our question, we have to design a circuit that detects three or more consecutive ones in the input line. Let us consider this will be our input. So the output will be of, when the input sequence detects three ones. So first one, second one, third one. The output will be of 1, right? So then the first one will having 1. So 0 1. It is not a pattern. So again 1 0 1 0. So far we didn't receive any pattern. So now look comes here. So again three ones are coming here, right? So we'll get output at 1. So all other places your output will be of 0. So all other places output will be of 0, right? So whenever we'll getting three consecutive ones, we'll get the output as 1. This is for of non-overlapping sequence detector. If it is a overlapping sequence detector, then the output for overlapping sequence detector is, look at the first one, 1 1 1. So first we'll get three consecutive ones, we'll get 1. Then the first set I will mark in different color so that you can able to identify easily. So here this will be of one set, right? So we'll get the output as 1. Then I'm going for another color, that is, if you look at this also a three consecutive ones, right? Here you can possible of getting the output 1. This is for an overlapping sequence detector. This is for non-overlapping, right? So this was the thing between, this was the difference between one overlapping as well as overlapping sequence detector. At all other places again 0 0 0 0 0. So now comes here again three ones are coming, we'll get the output as 1. So here it was no repetition, so all will be of then 0 0, right? So here it was not, nothing was specified. We'll go for an non-overlapping sequence detector. First we'll design, then we'll proceed with the state table as well as the state diagram, then we'll go for a design part. Okay. Okay, so this was the concept of overlapping sequence detector as well as non-overlapping sequence detector, that was given on the title slide itself. Okay, fine. So now, so we have to design a circuit that detects three or more consecutive ones in the input line. So whenever we are receiving, keep in mind, whenever we are receiving three consecutive ones, our output should be of 1, right? So for that, first I'm defining some states. So S naught is my first state. When I'm giving 0, when I'm giving 0, output will be at the same state, right? The output is 0. When the next one is coming, right, it moves to next state. When my input is 1, my state was changed to but still my output is 0. So keep in mind my output is 0 because so far I received only 1 once. Here the input is 0, right? So when only 1 came, so hence my output is 0. Next, if again I am giving the another second one, my output state will be moved to S2 state. Still my output will be of 0, right? Now so far we received 2 ones. If one more ones come, my output will be of 1, isn't it? If I'm getting one more 1 as input, my state is S3 state and my output will be of 1, right? So look at, I will repeat. The first initial state will be 0 input will have a 0 output. When my first sequence, my first input is 1, you won't get output, right? So because we have to design a circuit in the way that, such a way that we have to receive 3 ones, and normally my output will be of 1. So my first one input is giving, output will be of 0. Then I'm giving second input as 1, still it is 0. When I'm getting third input as 1, my output will be of 1, right? If I'm giving 0, then my output will move to the initial state, that is a S0 state. Okay, right? We'll have some more combination of here. So for suppose let us consider the first one is 1. At this S1 state, if my input is 0, then it has to move back to this initial state, right? But my output is 0. Okay, if currently I received only 2 ones, my output is 0. If at this state, if I'm receiving 0, then it has to move to the S0 state. My output is 0. Got it? Because since we are dealing with a non-overlapping sequence detector, we are not discussing now. We are discussing non-overlapping sequence detector, not an overlapping sequence detector. Okay. If at this stage, if all 3 ones are come, if again one more one comes, then it will be written at the same state. So 1, 2, 3 ones came, right? So already if 2 1 came, still 1 1 came in, so we are getting 3 input as 1. So my output is written at the S3 state. Okay. So now after this, they are going to assign a state. So state assignments. State assignments. This is useful to do the state table. I am assigning S0 as 0 0, S1 as 0 1, S2 as 1 0, S3 as 1 1. Right, these are state assignments I am assigning. Okay. Next we'll move to the state table. With the help of this state diagram, we'll move on to state table. Right. In state table, you know what are the things to be there. So state table, I'm writing my present state. Present state, then input, then next state, then outputs. We have to design a circuit, right? So we need a flip-flop inputs. So flip-flop inputs. Now I'm assigning my present state, let it be of A as well as B. My input I'm mentioning as X. My next state, if this is A, then the next state will be of definitely A plus and B plus. I'm representing output as Y. Whatever you want, you can take. Right, flip-flop. Here in the question, it was nothing of about flip-flops. Nothing was specified about the flip-flops. Hence, I am considering D flip-flop. What do you mean by D flip-flop? D is nothing but a delay flip-flop. Right. Okay, this was the thing. This was the state table that we are going to form now. Right. Now I'm writing the present state 0 0 and input is 0 0 1 sorry, 001, 010, 011, 100, 101, 110, 111. Right? When my present state is 00, at the time I am going to check for both inputs. Let it be of x as well as that x is equal to 0 as well as 1. Right? This is our first combination. Second, this is for third, and this is for fourth set. Okay. Now I am going to check for next state. So how you are going to obtain this next state? This can be obtained based on the present state along with the input with the help with the next that we are going to analyze what will be the next state, right? Now this is s naught. Keep in mind your state assignment is s naught is equal to 0 0, s naught is equal to, sorry, s1 is equal to 0 1, s2 is equal to 1 0, s3 is equal to 1 1. Now go back to the state table. My initial state is, that is s naught, that is this will be of a b here. Okay, my initial state is 0 0. So 0 0, when I am giving 1, it moves to s1 state. S1 state value is 0 1. Hence I can write here, if it is when first we'll go by line. My present state is 0 0. When my input is 0, what will be the next state? So s naught is 0 0. When my input is 0, it will return the same state, that is s naught again, that is equal to 0 0. So I am writing here as 0 0. What was the output? Output is also 0, right? Next comes to the second point. My input is 1 and my present state is 0 0. So 0 0 represents s naught. When I'm giving 1 as input, it moves to the next state, that is s1 state. The corresponding value for s1 is 0 1, but the output is 0. So this is moved to 0 1 and my output is 0. Next comes to present state 0 1 and my input is 0. So 0 1 is nothing but s1 state, right? When I am giving 0, it go back to the first state, that is initial state, s naught, that is 0 0. 0 0. My output is also 0. Next 0 1. When I am giving 1 as input, it moves to the next state, that is s2 state, but still my output is 0. So s1 to s2, s2 is 1 0, but still my output is 0. Now s2, that is 1 0. So 1 0 is my input. When my 1 0 is my present state, x is the input. 1 0 is s2. So 1 0, when I am giving 0 as input, it go back to the initial state 0 0. My output is still 0. So 0 0, this will be of 0. Next, again s2 state, when giving 1 as input, s2 state, when 1 as giving as input, it moves to the s3 state, right? When 1 0 1, my output is 0. Okay, next comes here. So now we are at 1 1. My present state is 1 1. When 0 is giving us input, 1 1, when 0 is giving us input, it moves to the initial state 0 0, but at the time my output is 1. 0 0, my output is 1. Next, already I am having a 3 1s and my output is 1. Still my next state, the present state is 1 1. When I am giving 1 as input, present state is 1 1. When I am giving 1 as input, it will return at the same state, that is s3 state. The s3 state text state will be represented as 1 1, and the output is also 1. Now how to write this flip-flop inputs? With the help of excitation table. So we have to know the excitation table for D flip-flop. I will write here. I'll write in some other color so that you can able to identify. Right. So excitation table for D flip-flop. So what is it actually? So Qn plus 1 it is in D flip-flop, right? So 0 0 0 1 1 0 1 1. So when both are 0, output is 0. I mean the input is 0 0 1 0 1, right? So with the help of this excitation table only, we are going to write this flip-flop inputs. Now for this, we have to compare A with A plus. If both are 0, our output is 0. Similarly, I can compare for 0 with 0, that is B with B plus. Both are 0, we'll get 0. Okay. Next, we'll compare A with A plus. 0 0 means it is 0. Next time compare B with B plus. If it is 0 1, then you can go for the excitation table second row. The output is 1. The similar way, you can write all the flip-flop inputs: 0 0 1 0 0 0 1 1 0 0 and then 1 1. Right? Like this, we have to obtain the flip-flop inputs. Right? This is actually an excitation table. Without knowing this excitation table, you cannot able to design a circuit. Okay. Next, so after obtaining this state table, we have to draw a K map for getting the expression for output as well as flip-flop inputs. Getting the outputs as well as flip-flop inputs, that is DA as well as DB. Okay. Okay. With the help of this present state and input as inputs to the K map. So we'll have since we're having three inputs, so we'll have a K map, three variable K map. So we'll have A as well as BX 0 0 0 1 1 0 1 1. This is 0, this is 1. Okay. So where you are having 1, so only 1 1 0 and triple 1. 1 1 0 and triple 1 we are having 1. Let's group this. What will be the expression for K map? Output Y is equal to, so A into B. So is the K map expression for the output Y. The similar way we have to get the output, get the K map for DA as well as DB, right? So for DA, here you can note Y. Next we will have an DA. Next we will solve for DB. So we solve for DA, then three variable K map. So same A BX as the input. So 0 0 0 1 1 0 1 1. This is 0, this is 1. So 0 1 1 1 0 1 0 1 1 1 0 1 as well as triple 1. I'm going to group like this. The first 2 bit table I'm grouping, another table I'm grouping. So I can get D is equal to BX plus AX. So this is the input for the first flip-flop. Then you can go for DB. It's a 3-bit variable, input variable came up. So 1, 2, 3, 4. So again the same A BX, right? 0 0 0 1 1 0 1 1 0 with 1. Now comes to flip-flop inputs DB. So 0 0 1 I'm having 1. 0 0 1 it's 1. Next where we are having 1, 1 0 1 1 1 0 1 I'm having 1 and triple 1 I'm having 1. Now group this two variable, again group this two variable. From this you can write dB is equal to AX plus B bar X. So this is the expression for the second flip-flop inputs DB. So after obtaining this scheme-up expression, now we are going to design a circuit. We are going to draw a logic diagram with the help of these inputs, right? So first I'm drawing flip-flops here. So two flip-flops I'm drawing. First flip-flop. So second flip-flop are drawn. So input is DA and the output is QA. The component is QA bar. Here this is DB. This is QB. This is QB bar. Right? Right. What was the input? Okay, let us have an output. Output is actually A into B. So A into B. So hence I am using an AND gate over here. So I'll get an output Y is equal to A dot B. Okay. So now we got output Y. Now what about the inputs? Input is equal to Bx plus Ax. So what was the X here? So we'll have an X is my input, and I have to use for D I have to use AND gate as well as the OR gate, right? So I'm going to have so X was here. So I'm going to have one AND gate. So for that, what is the first input? Is B as well as A. Okay, can get the second input is output. So now here it is AX. Now this has to be added with an OR gate. So the other input for OR gate is then one AND gate. So my AX was over, then BX. So again this X has to be connected, and the other input is B. So B is my another input. So now here this is BX. So this was added and that was given as input to the first flip-flop, that is A flip-flop. Okay, then the next. So DA from first input is over, and second thing I need to have an X as well as X naught. So for AX I can get from here. So this I need AX, right? So I have to get from so I have to get from here. The first, because for the first flip-flop I'm using the same one, hence I can take from here. So AX was got in. Then we need B bar X, right? The another input is B bar X. So for now to get a B bar, this is B. I need to use an inverter. So here you're having B. I need to have an inverter. So NOT gate, that is NOT gate. I'm using NOT gate over there. So this is B. Here I can get B bar with X as another input. So B bar X. Here that was connected as one of the input to the OR gate. So this was connected to the D flip-flop. This is actually an B bar X. This is B bar. Okay, now we can get some idea about this D flip-flop's implementation. Yes, that's all about the logic diagram of the sequence detector with 3 consecutive ones. Okay. So I'll repeat the entire thing. First thing, so design the question was given as design a circuit that detects three or more consecutive ones in the input line. So we have two things, non-overlapping as well as overlapping, that we discussed, right? Okay. If three consecutive ones repeated at the input, my output should be of one, right? The thing, keep this in mind. Then I'm writing the first state as 0 0 for writing the state. This is a state table. You can use any flip-flops for implementation. For simplification purpose, I choose an D flip-flop. If you want to implement in JK, you can able to implement in JK, or if you want to use a T flip-flops, you can use it, right? So whatever excitation table you know, use that excitation table, uh, and then proceed with the logic diagram implementation. Okay, the first state I'm assigning is S naught is 0 0. Okay, so at initial state, S naught is considered as an reset state. When I'm giving 1 as input, it moves to the next state, that is S1. When again I'm giving 1 as input at this stage, it moves to the S2 state. But still, look at this, outputs are all 0 because we didn't receive any 3 consecutive ones. At this stage, if I'm getting one more 1 as input, now I got 3 consecutive ones, the first one, second one, as well as third one. At this stage, that S3 state, I'm getting my output as 1 since I received 3 consecutive ones. Okay, if I'm receiving a few more ones there, then still it will be at the, my output is 1. Okay, if it is 0, if I receive at this state, it go back to the reset state. Okay, so the first thing. Then second thing, at S1 state, when 0 is given as input, at the time it go back to the reset state. Suppose if consider for S2 state, after receiving two ones, if I'm receiving 0, then it go back to the again reset state. Okay, so after obtaining the state table, we have to use the state assignments. I am assigning S0 as 0 0, S1 as 0 1, S2 as 1 0, and S3 as 1 1. Okay, now come back to the state table. Present state, input, next state, output, as well as flip flop inputs, right? In present state is AB. I'm representing AB. If you want XY, whatever you want, you can choose. For our convenience, I chosen AB as present state, and input is X. Next state is A plus B plus, and my output is Y. And flip flop input is I'm going to design with the help of D flip flop. Hence, I'm choosing such DA as well as DB. Okay, I'm writing the possible combination. So 0 0 with 0 as input, 1 as input. Similarly for 0 1, for 1 0, as well as for 1 1. The next state I'm obtaining from this state table with the help of input. If with the help of the state assignment, so 0 0, if 0 is giving, it was written at the same state. So 0 0 is giving, it will be next state is 0 0, but the time output is also 0. In the similar way, I wrote for the state table. Then for flip-flop inputs, I need an excitation table to compare with present state as well as the next state. That is QA, that is QA and QA plus. Okay, or in some other words, A, this is A plus. So with the help of this Q1 and Q1 plus 1, we are going to get these T flip-flop inputs. Right. Now I'm going to compare this 0 with the next state. So both are 0. Now look at the excitation table. Both are 0. We'll get 0. Look for some other combination. So B is 0 here and B plus is 1 here. So 0 1, my output is 1. Hence I wrote 1. So in a similar way, I wrote for the flip-flop inputs with the help of excitation table. After obtaining the excitation table, I can go for K-map now to get the expression for output as well as the flip-flop inputs. So it says since it's a 3-variable K-map, I'm getting the expression as Y is equal to AB, DA as well as DB. So after getting this expression, I'm implementing this with the flip-flop inputs. So one thing was missed. I missed here the clock pulse. So clock pulse is must. So I'm designing for a synchronous clock pulse. So clock pulse you need to give, right? So first flip-flop was implemented. As well as second flip-flop. This was my output y is equal to a dot b. Any doubts? You can raise the question. Okay. Thank you for listening.